pump water and sand and a mixture that helps hold that together to actually crack the rock, create fissures in that rock. The sand holds those fissures open, and that allows what would otherwise be very difficult to produce reservoirs, allows them to give up that gas.
And there are chemicals that go down with that mixture, right?
There are. So there's a couple of things to keep in mind when we talk about that. One is that the zones that we're drilling into are hydrocarbon-bearing zones. You know, there's a lot of chemicals in hydrocarbons, of course. When we drill these wells and do hydraulic fracturing, it's about 99% water and sand, and it's about 1% other materials. And those other materials are things like a gelling material, guar, gum, things like that. But it also includes some chemicals like ethylene glycol, like you'd find in antifreeze. But I think everybody's big concern is with those chemicals and with the chemicals that naturally occur in a hydrocarbon-bearing zone is how do you keep that isolated from the water that we all draw from, the shallow water tables, as opposed to the very deep hydrocarbon-bearing zones.
And how do you keep it isolated? Is the reason that you believe it's not dangerous that the actual fracturing happens so far below the water table?
Yeah, hydraulic fracturing tends to get the headline around this issue, if you will. I mean, that's everybody's concern is that we're going to crack this rock and somehow fracture into the water table and then allow those two to communicate. That's physically impossible to do, actually. I mean, because the water table goes down to, let's say, 1,000 feet plus or minus below the ground, sometimes deeper, sometimes shallower. As I said, these reservoirs we're drilling into are a mile or more deeper into the ground. So physically, you actually can't fracture over those sort of distances. And what we do is keep those fractures within the producing zone itself. So while it receives most of the attention, the real concern that people ought to have, and the concern that we have as someone that operates in this business, is when you drill through a water zone, and then you drill down into a hydrocarbon-bearing zone, it's actually that well that has now connected the two. It's like putting a straw between the two. And so how you build that well is absolutely critical. And that how much integrity that has depends on the number of layers of pipe that you put in place, how you seal that pipe against the formation, and how you absolutely prevent those hydrocarbons from ever touching that water zone. That's the critical element.
Does the oil industry have a plan B in place just in case there were some unanticipated way that the water table did somehow get contaminated?
Yeah, so I mean, one of the interesting things that we're doing here this week at Aspen is we're rolling out what we call our natural gas development standards. And we're doing this in direct response to some of the concerns that are out there about how this business and this resource gets developed. And so the idea of having an emergency response plan is absolutely part of that. So having a clear plan that fits the geology, the topography, the residential status around a development, the water table status around a development, all of that exists before you ever go in and drill a well. When we think about things like the water table and protecting it, when we move into an area to develop natural gas, the first thing we do is drill a water well and test the water, because you need a baseline understanding of where the water is. And then we'll drill our well, we'll start to produce gas, but we'll keep that water well in that monitoring capability. So despite the multiple layers of protection that we put in when we drill these wells, we're constantly monitoring the water and the physical conditions of the well just to make sure that there's no problem.
But if there is that Gulf disasters kind of contributed to the concern about fracking, do you think that people wouldn't be so worried if it hadn't been for that?
I don't know. I mean, I think there's a series of things that have happened in the last decade. The nuclear disaster in Japan, the oil spill in the Gulf of Mexico, that I think is created an atmosphere of even less trust for companies and how they do business, and particularly how they would do business if they're not well regulated. So I sit here in a business that potentially can have an impact, and how we do it is important to ensure that we don't have an environmental impact. And I sit here very happy to recognize that risk and to have it heavily regulated, to have it monitored, and to actually be very transparent as a company in terms of how we do it and how our actual operations are going, which again is why we're here this week being very transparent about those principles and ways of doing business.
I know a lot of people are so excited in a time where we have a lot of energy, problems and worries about where we're getting our energy from. People are excited about the vast reserves of gas that we'll be able to tap through this technique. But I also know a few years ago Shell, I think, overestimated some reserves. This time around, are you pretty confident in the gas that you think is available?
Yeah, there's been a recent New York Times article that challenged exactly that. Are these resources real? Because if you talk to us, if you talk to the EIA, the Energy Information Agency, associated with the U.S. government, the estimate is that we've discovered enough natural gas to provide over a century of supply to the U.S. And so the challenges around that are not very well founded. I mean, we've drilled enough wells now, and this is very geographically dispersed, if you will, across the U.S. and Canada. We've drilled enough wells now to where we understand pretty clearly what these resources are, how much can be recovered, and what the economics are with recovering that. And so I capture gas.
Consisting of a number of high-pressure pumps and blending equipment. This equipment will pump a mixture of water and proppant, usually sand, through the newly created perforations in the production casing and into the shale formation. First, water is passed from a water storage impoundment into the blue working tanks depicted on this location. The water is then pulled into a hydration unit, which provides the ability to gel the fluid before it is transferred to the blender. At the blender, proppant and a small amount of chemicals that aid in the fracturing process are added. The blender transfers the fluid and proppant mixture to the pump trucks through the low-pressure side of the manifold. The fracturing pumps increase the pressure of the fluid, sending it back through the high-pressure side of the manifold to the fractory where it enters the well. The entire fracturing process is controlled from the treatment monitoring van. When the fracturing fluid reaches the perforations, pressure builds until the shale formation fractures, allowing fluid to enter into the formation. Additional fractures are created along natural zones of weakness in the shale. These fractures are contained within the shale formation, well below the ground. After an initial stage of fluid called the pad is pumped to create a fracture area, proppant is added to the fluid and is distributed throughout the newly created fracture network. At the conclusion of the fracturing treatment, the proppant allows the fractures to remain open so that the natural gas can flow into the production casing and to the surface. This completes the first of several stages in the fracturing process. This process is repeated by lowering and pumping down an isolation plug and perforating guns into the wellbore to complete the next stage of fracturing. This time, the tools are conveyed into the well by a wireline unit, which allows the fracturing process to proceed much faster and more efficiently. A lubricator is used to control the pressure of the well while the operation is taking place. On the bottom of the perforating gun, a composite bridge plug is placed to isolate the newly fractured zone. This ensures that the subsequent fracturing treatment is contained in the current zone. The perforating gun is again fired at roughly 50 to 80 foot intervals, creating a connection between the production casing and the shale formation. The fracturing process is then repeated until all of the stages are completed. A typical shale well has approximately 8 to 12 stages of fracturing. At the conclusion of the fracturing operations, the isolation plugs are removed from the well and production can start. The produced fluids are diverted through a flowback manifold into storage tanks. The fluids are then recycled or disposed of according to state and federal regulations.